Okay, so work as a dot product. We just learned the other day that work is force times a change in direction times cosine of an angle, right? You guys, you can put R here, you can put S here, you can put X here, you can put Y here, just whatever will make you know that that's a distance, okay? So force times change in distance cosine of theta. That is what we learned. Now, previously in the year when we did vectors, we were adding and subtracting vectors. What are we doing here? Yeah, we're multiplying vectors, okay? So when you multiply vectors, one of the ways that you do it is called the dot product, okay? This is what the dot product looks like. So let's say vector A, maybe that's our force, dot vector B. That could be our displacement, okay? Now, you have to write it this way. This and this are two completely separate things. They are not the same. You have to have that dot there, okay? That is very, very important. And what the dot product gives you is A, B, cosine of theta, just like we see right there with what we derived as our equation for work. Other than a dot product, sometimes this is called a scalar product. So those are the two names for it, dot product and scalar product. So what the dot product is going to depend on is the orientation of the two vectors that you're focusing on, okay? So there's technically 5 different cases of dot product that we're going to have. And 3 of them are considered special cases, okay? So one of our first cases would be basically if vector A and vector B are parallel to each other like this, and they're pointing in the same direction, okay? What do you think theta is here? Yeah, it's 0 degrees, okay? And when theta is 0 degrees, what do you think the dot product of A and B equals? It's just going to be AB, okay? So we're going to consider this one of our sort of situations or orientations that we're going to be dealing with, okay? The next one is when our vectors are like this. That means that when theta is less than 90 degrees, okay? So when theta is less than 90 degrees, our dot product is going to be greater than 0. So when our theta is less than 90 degrees, our dot product should be greater than 0. Our third case is going to be when we have a 90-degree angle between the two vectors. Okay? What do you think the dot product is when we have a 90-degree angle, if you had to guess? Mm-mm. It's just going to be 0. Whenever work is perpendicular, it's always 0, okay? So whenever work is perpendicular, this rule of the dot product lets us know that it's always going to be 0 whenever the force is perpendicular to each other. So for instance, I think we talked about this a little bit the other day. Remember when I was holding my Kindle when we did this, but I don't have it with me today. I was holding it, right? And I said, okay, am I doing work? Am I doing work on this? No, I'm not. Because I'm moving. What way am I pushing up on this right now? Up. But what way am I moving? To the side. So my force is perpendicular to the movement. Now, what if I do this? Am I doing work?
Yes.
Now I'm doing work, okay?
So would that be considered that the friction was doing work? The friction on your hands? Because it's what's moving it.
There's just no work. There's no work at all. Because it's not moving anywhere. Friction would be doing work on like something that's sliding.
Static friction.
It'd be doing negative work. Static friction?
Yeah.
I mean, static friction would come into play like if I were like tilting this. But when it's just like this, it's just the force of my hands holding it up. Okay? The next case number 4, is when our angle is what, you guys?
Longitude.
Yeah, when it's greater than 90 degrees, okay? But less than 180. Greater than 90, less than 180, okay? When that's the case, our dot product is going to be less than 0. What do you think our final one has an angle of?
Greater than 180. No. 120.
What do you think? When it's 180. So when theta is equal to 180 degrees, okay? When theta is equal to 180 degrees, the dot product is negative AB. So that means that our 3 special cases, you guys, our 3 special cases are at 0 degrees because we know it's just going to be AB. At 3 degrees, at 90 degrees because we know it'll be 0, and at 180 degrees because we know it'll be negative AB. These aren't considered special cases because, well, isn't the range of the number that they could be sort of a lot bigger? Yeah, okay. So these are our 5 cases for dot products or for work, okay? So far, so good? You guys want to do an example?
Sure.
Sure. Woo.
You don't get a choice.
No, you really don't get a choice. I mean, if you say you don't want to do an example, I guess you can just like struggle through it on your own. Okay. So let's say we have vectors A and B. And they have an angle of 30 degrees between them. Vector A has a magnitude of 3, and vector B has a magnitude of 4. Okay? We know that A dot B is going to be A, B, cosine of our theta. And should the result that we get, should it be greater than 0, less than 0, equal to 0? What should it be? Should be greater than 0, right? So you guys want to let me know what we get? We're going to have 3 times 4 cosine of 30. That is wrong. Are you sure you're in degree mode and not radian?
I have 10.39.
10.39 is right.
Yeah.
Awesome. Okay. Does that example, does that make sense? Why we did that? How we did that? Yeah? Okay. So for this next part, do you guys remember when we were doing some stuff with I hat and J hat? Vaguely?
Yes.
Okay, so we did some stuff with I hat and J hat, okay? And they're going to come back into play again. So something that we're going to want to remember, because we've probably forgotten, is that if you have two I hats multiplied together, do you think they're equal to 1 or 0? If you have them dotted together. Yeah, they're going to be 1. What about a J hat and a J hat? 1. What about an I hat and a J hat? That's going to be 0, okay? So we're going to sort of want to keep this over here to remember that while we continue talking about some ideas behind the dot product. Okay? So the other way that you can think about dot product is like this. We've got A dot B, right? And each of these, when we've looked at them up here, don't they have an X and a Y component? Because they're vectors, right? So you can look at these like AX. Do you remember if X is I hat or J hat? Do you remember? It's I hat, okay? Plus AYJ hat dot, I tried to put an A again. Those are the same thing, okay? Because since they're vectors, they have X and Y components. Now, every now and then, can one of the components be 0? Yeah, totally, okay? But that's sort of our general idea. And what you're sort of supposed to do with this is distribute, okay? So let's try that. We're going to get, you guys know how to distribute, right? We're going to do AX times BX. Okay, do it at your seat. See what you get. I'm going to do it up here. See if you guys can recall your distribution days. Distribution days. Did you guys get to a similar place? What's your question?
So when you simplify that, it would just be AX times BX plus AY times BY.
Right on the money, okay? What Ian said is that, these things are going to go to 0 because we know J hat dot I hat is 0. And we know I hat times I hat dot I hat is 1 and J hat dot J hat is 1. So you end up with AX BX plus AY BY. So we're also going to do an example where we would want to use this method instead of this one, okay? So somewhere we might want to use this is let's say that we are given two vectors, okay? And we're told that vector A is 3i hat plus 3j hat, and vector B is 4i hat minus j hat. Were you given an angle here? But they obviously make some sort of angle, possibly. Something's going on with them and you want to dot them together, okay? So are we going to be able to use this method? No, we're going to want to use this method. So how would you go about plugging this in? What would be our AX? Would it be 3i, or do you just have to put the 3, right? And then what's our BX? 4. Okay. What's our AY?
3.
And what's our BY?
1.
Is it 1?
Negative 1.
Negative 1. Okay. So we've got 12 minus 3. So what do we get?
9.
9. So if you had to guess something about this angle, would you say that it's at 0, that it's greater than 90, less than 90, 90? What would you guess? It's going to be less than 90 degrees. Why? Because it's positive, because it's greater than 0. Okay? Still so far so good? I told you guys dot products weren't going to be bad, right? Pretty nice. Can I erase this? Yeah? Okay. You got a new iPad?
Yep.
How much was it? How much was it?
1,200.
Huh?
1,200.
Is that the rest of your random lot of money?
That's why we have 2 kidneys.
That probably
Okay.
was it a good investment?
Thanks. Okay. So we're going to do another example of calculating work using the dot product, okay? So let's say we have a 70 kilogram skier, okay? And they're gliding at 2 meters per second when they start down a slippery slope that's 50 meters long, and it's a 10-degree slope. We want to know their speed at the bottom. We're going to draw a picture. Yeah. So we've got somebody skiing, right? They're on a slope. The slope makes an angle of 10 degrees with the ground, okay? And they're starting out up here on their skis. Okay? They're skiing down. And they're eventually going to end up at the bottom. Okay? Now, when they start out, they have an initial velocity of 2 meters per second. This person has a mass of 70 kilograms, and overall, they're going a distance of 50 meters. So we'll call that delta R, 50 meters. And we want to know what is the speed at the bottom. Okay, and we know from doing all this dot product stuff, right, that work is going to be force delta R cosine of theta. So let's start trying to sort of pick this apart a little bit, okay? First things first, how do you think we'll find our force?
Mass and acceleration.
Yeah, mass times, what's our acceleration?
Gravity.
Gravity, okay. So we'll say mass of 70 kilograms times 9.8. Okay, so can somebody tell me what the force we're experiencing here is?
686 newtons.
686?
Yes.
You guys agree with that?
Wait, we have to solve for like the different components of gravity.
No.
Wow.
Here we don't. Don't worry, we'll get there. Because it's just a force. It's just an arbitrary force. That's the force that's always acting on it. Now, why we're not going to need to do that is because, you guys, what do you think our theta is?
10 degrees.
Mm-mm.
No.
Okay, so how you have to think about this is we're going from here to here, right? We've got a 90-degree angle at play with like basically our normal force and this, and we of course had our gravity pointing straight down. Now, what force did we use here, you guys? We used the force of gravity, right? Because that's our easiest one. So we need to take a second and think. Is this the angle that we need?
No,
What angle do we need?
we need to angle the gravity force to the direction.
Yeah, we need this angle right here.
So that's 80 degrees.
So that's 80 degrees, yeah. So we're going to want to use a theta of 80. Does that make sense to everybody?
Yeah.
Yeah? Okay. So when we plug this in, we're going to want to have 686 newtons times our delta R of 50 meters cosine of 80. So what do we get as our work?
Joules.
5,900 what?
56.13 joules.
All right, are we done?
No.
No, what were we asked to find?
Final velocity.
Final velocity. Okay, so I'm going to add to our knowns up here that the work being done is 5,956.13 joules so that I can clear up some space down here to do the rest of our math. Okay. What else do we know that work is equal to?
Mass or force times distance traveled.
Change in kinetic energy. Remember, that's one of the other things we derived, okay? And the change in kinetic energy just so happens to have velocity in it. Right? So, since that's the change in kinetic energy, I can just say that work is equal to that. And now we need to rearrange to solve for our final velocity. So, what do we need to move around, you guys?
You need to add 1/2 mv squared to the other side.
Mm-hmm.
And then divide by 1/2 m.
Which is the same as multiplying by
Multiplying
what?
by 2 and dividing by m. And then you're going to take the square root of all
There. That's what you guys want me to do, right? So what do we end up getting as our final?
that.
That's what you guys want me to do.
Yeah, that's right.
You're supposed to multiply everything on the top by 2.
I did.
Well,
2
yeah,
times
there's
W.
1/2
2
of
times
that.
1/2 is 71.
Yeah, never mind.
I mean, there is one way you could further simplify it if you wanted to, but you don't have to.
We got 13.2 exactly.
Yeah, I got that.
13.20 meters per second. Awesome, you guys. Good job. Any questions about this one? Yes, Josh.
Where did the 80 come from?
The 80 is coming from that we need to get the angle between our, basically the way that we're traveling and the force that we use. We use the force due to gravity. So the vectors that we're dot producting together are the force of gravity and our displacement vector.
Wait, so could you like, if you were to, could you solve for like a different force and use cosine 10? I mean, that'd probably be harder.
I mean, if you wanted to, it's going to be more work for you though. But whatever force you solve for, you're going to need to find that angle in relationship to the displacement vector.
You, how did you get that the angle was 80 degrees?
Jacob, how did you get that the angle is 80 degrees?
Because we're looking for the angle relative to the direction you're traveling.
Okay, so how did you know it was 80?
90 minus 10. Because theta is 10. You subtract that from direction relative to the ground. Because normally gravity is pointing straight down, so that would be 90 degrees relative to where you're standing. But since he's already 10 degrees down, you subtract 10 from that.
And it gives you your answer. Awesome. Okay, any other questions, you guys? No? Then we're going to talk about situations where zero work is done. And you should have run into a fair amount of zero work on your problem set yesterday.
Wait, so that means I wasn't wrong?
Yeah, I was afraid I was wrong.
That always makes it a good segue into this. So yes, there were multiple places where you should have had zero work on your problem set yesterday, okay? Now, there are 3 situations where we're gonna have zero work, all right? The first one is when the object doesn't move. So, object doesn't move. Why might we have zero work if the object doesn't move?
Because work is equal to distance traveled times force.
Yeah, and if there's no distance traveled, it's going to be 0, right? Okay, the next one is one that we just saw today, which is when the force is perpendicular. The third one is one of your guys' favorite things. Uniform circular motion. Okay? And uniform circular motion and perpendicular force go hand in hand. Okay? Because if you think about it, if you're right here, that's your displacement, right? You're going tangential along the circle, and then your force is inwards, so it makes it perpendicular. But sometimes it's easier just to remember that uniform circular motion in general, you're not gonna have any work being done, okay? So one of those situations where people are the most tempted to say there's work being done when there isn't has a lot to do with this object doesn't move thing, okay? And why they do, and I'm sure you guys, you're not gonna struggle with it, but it sort of makes sense. For instance, I cannot push this thing, okay? It's not gonna budge. 1, it's heavy. 2, it's attached to the ground. It's just not gonna move. But if I continue to push on this for a few hours, probably even take a few hours, I would start breaking out in sweat. I'd be tired. I'd be fatigued, okay? People struggle to realize that I'm not doing any work because in their eyes, it looks like I've done work, right? But have I done work? No, because has anything moved? I've accomplished nothing. Exactly.
So something needs to change for
The position's going to have to change of the object in order for work to be done.
the position shows that it's either like gaining energy or energy is being pushed.
Yeah, because since it's also the change in kinetic energy, what was this thing's velocity before I started pushing on it? What is it when I give up? 0. So have I done anything? Have I changed the energy at all? No. I haven't. Okay. So another thing, I know you guys are like another thing, right? So variable force. So far, everything we've done has had a pretty constant force, right? But this wouldn't be calculus-based AP Physics if we didn't have a variable force. With our variable force, work is equal to the integral from the initial position to the final position of Fs dx. However, if the force is variable, can we bring out the force anymore as a constant? No, because it's going to keep changing, okay? And what it is, how we find our variable force, it's the area under a force versus position graph.
Sounds familiar.
So you no longer get to take the force out of the integral. It's no longer considered a constant. So let's start with a pretty basic graph to sort of get our feet wet with this, okay?
Battery's low.
Well, how long did the battery last?
I got a bunch of classroom notifications in my person.
Classic.
The batteries, it started at 100%, it's at 5% now.
But when did it start at 100%?
Beginning of class.
Oh, God. That's for paying
Not
$1,200.
5%, I meant 95%.
Oh, okay. I was like, that's a really bad battery for paying $1,200.
It's like that, like 80%, right? So it's pretty good. 5%.
Classic iPhone 4 delay.
All right, so this is our graph that we have, okay? The graph is representing a car. The car has a mass of 1,500 kilograms. And it's getting towed. It starts from rest. And we want to know what its final speed is after it's been pulled for 200 meters. So we've got position and we've got force. Okay? So, if the car is getting towed, what kind of force do you think it is?
Tension.
It's tension. Good job, you guys. So, we're going to say that work is the integral of Tx dx here. Because our force is tension, and we're moving in the x direction because we're getting pulled horizontally, okay? And we also know that work is equal to the change in what?
And area under the curve.
This change in what? Kinetic energy. Are one of these terms equal to 0?
Yes.
Which one?
The initial.
Yeah, this whole thing. Bam, 0. Okay, so that means that the work can be set and the area under the curve can be set to 1/2 mv final squared. But we're trying to find v final, aren't we?
Couldn't we also just do like geometry to find out?
That's what we're going to do, yeah.
Okay.
So in order to find the work, what are we going to do? Find the area of a,
Curve.
which is a triangle, right? How do we find the area of a triangle?
Base times height times 1/2.
Yeah, 1/2. What's our base?
Oh god.
200.
What's our height?
5,000.
Okay, so what's our work here?
About 500,000.
Yeah, 500,000 joules. Bless you. Okay, so now we have our work.
Wasn't it asking us to find the work
We were asked to find the final velocity after 200 meters.
On the things.
So how are we going to rearrange this to solve for final velocity?
Multiply by 2, divide by n, take the square.
Ding, ding, ding. Okay, somebody tell me what the final velocity is after 200 meters. What are the units? Yep. I can barely hear you, but you're right. 25.82 meters per second. You guys have any questions about this one?